Hello everyone. Today we're starting our third unit. This is our introduction to proofs, and you'll find that we're going to be working with proofs in both Unit 3 and Unit 4. And proofs are a very different kind of math that you haven't encountered before. We usually think of math as like drawing diagrams like triangles and squares and marking them up, or setting up an equation and solving for the variable. And while all of that is good, we'll be doing less of that in this unit and be focusing on the connection of ideas. When we are talking about proofs, we're talking about connecting ideas in a logical, sequential manner. So, to talk about that, we need to first of all start off with statements, because we're going to express these ideas through statements, these conditional statements. So today it's going to feel more like an English class as we're talking about how we're going to be writing our statements, and really kind of using this as a way to create the building blocks for expressing the ideas that we will then connect together to create the proofs that we'll be doing in the days to come. All right. So with this, we have a little bit of a little biography here. Goldberg created cartoons much like this, and the reason why we are using this as a way to talk about proofs or introduce proofs is because we're focusing on the fact that each of these ideas occurs one at a time, and there's always a cause and effect. One idea leads to the next, or one action leads to the next. So here we're starting off with A. This is where it is. This guy with the long hair happens to tickle the chin of the mule, and because the mule is tickled, he then kicks, and because he kicks, he then hits this spoon, and because the spoon is moved, it squirts grapefruit juice into the eye of the guest, and then the guest is now reaching for the napkin, and the napkin, which in turn is going to cause this pulley to turn, and this pulley is then turning the screw, and the screw then rotates the barber pole, which happens to have a paintbrush leading on it, and so the paintbrush then creates this barber pole stripe on the pole, and this guy with the long hair sees the barber pole, and it reminds him to get a haircut, and so that's what he calls this, as an automatic arrangement which reminds you to get a haircut. So notice a couple of things here. First, it's a series of cause and effect. And that's what proofs often are. Proofs are, here's the cause, and now here's the result of that. Or here's the given information, and now we can figure out what comes as a result of that given information. So we're connecting ideas together. Secondly, notice that only one idea happens at a time. You don't have two events happening at a time. It's a very clear process of one cause and one effect. Oftentimes when you are doing algebra problems in your head, you might be racing through and thinking through two steps and trying to write down maybe every other step to quickly get through the problem. Maybe you're doing two calculations in your head and you write down the result of that. We can't do that in proofs. In proofs, we're only allowed to write down one idea per line. We can't combine or condense those ideas. We can't smash them together. We have to write down every single step because it's about sequencing ideas. Not always algebra ideas, but it could be other kinds of geometric ideas. So what we're looking at here is just this kind of notation with the arrow symbol. That means imply. So A implies B. Again, you can think of it as this is the cause and this is the effect. So A causes B to happen. So A is the long hair on person A, tickles the chin of the miniature mule at B. So there's your cause and effect. Then, what we just ended up with, B, that mule, is now the cause for the next sequence. The mule, at letter B, is now kicking the spoon at C. Notice we don't jump from A, we don't go A implies B, and then jump to C. No, B is that linking part. So you can see how we have this sort of connection between what used to be the effect is now the cause for the next line. We're going to see something kind of similar with some of our proofs where the result of one idea leads to the beginning of the next idea. Anyway, there it is filled out for the rest of that little diagram, going all the way to letter I as we complete that particular diagram. So that's just a little bit of an introduction. Let's turn the page over and take a look at a bunch of vocabulary that we need for writing these statements. I'm skipping over example 2 here, where you can make your own invention. Let's go to the vocabulary, and I've already written these in just to save a little bit of time. I'll read it through and you can copy it down. So we're talking about statements communicating the ideas that we will be working with in our proofs, and these statements are called conditional statements. So a conditional statement is a logical statement that has two parts, a hypothesis and a conclusion. By saying logical statement, it has to be true. It can't be silly. But it has two parts, a hypothesis and a conclusion. Now the hypothesis is a word you've heard about in your science class when a scientist makes a hypothesis. This is something different. This is not your science class hypothesis. This means something different, and we'll talk about it in just a moment. Okay? We're going to format these statements in a very particular manner. We're going to put them in an if-then form. The if-then form is a form of conditional statement in which the if part contains the hypothesis and the then part contains the conclusion. So we have our conditional statements, which have two parts. There's an if part and a then part. So the hypothesis is the first part of the conditional statement, and it comes after the word if. We'll see some examples down here in a moment. The if word is not a part of the hypothesis. The hypothesis comes right after the word if. The conclusion is the second part of the conditional statement, and it comes after the word then. So let's use example 3 now to write down definitions of the following terms, but we're going to format them in this very particular if-then statement form. We'll then underline the hypothesis and circle the conclusion. You've done things similar in your English class when you've had to maybe underline the subject and circle the predicate, or subject and verb. So things of that sort. Here we're underlining the hypothesis and circling the conclusion. So when you think about perpendicular lines, you might just say very casually, oh, those are two lines that cross each other and form a right angle. That's in the general sense, but we want to be as accurate as possible, and we want to format this in this if-then pattern. So there are several correct statements we could create. This is just one of them. So here's the if part. If, this sets the stage. If two lines intersect to form a right angle, comma. Now we always separate the hypothesis from the conclusion with that comma, so you know what comes in the first part and what comes in the second part. So there's your comma. Then they are perpendicular lines. Now we've studied perpendicular lines before, so hopefully when you read this it makes sense and you would agree that yes, this is true. If two lines intersect to form a right angle, then they are perpendicular lines. So there's the if part, there's the then part, there's the comma separating them. That's how we know this is a conditional statement. It is conditional, meaning the answer, the result, depends upon the first part. In the same way that we had this cause and effect from this little cartoon where A caused B, we have this same idea where the first part is then going to cause the second part. This is the effect. So here's your cause. If two lines intersect to form a right angle, here's the effect. Then they are perpendicular lines. So we say it's conditional because it depends on this first part. If this first part was not correct, then we would not lead to this conclusion. If, for example, it said, if two lines intersect to form an obtuse angle, for instance, well, then they are not perpendicular lines. Okay? So that's why we call it a conditional statement. The first part must be true in order for the second part to result from that, cause and effect. Okay, we're going to now underline the hypothesis. We don't underline the word if. The hypothesis is two lines intersect to form a right angle. And then we're going to circle the conclusion. So we don't circle the word then. We're going to circle they are perpendicular lines. So there's your hypothesis and your conclusion. We've studied parallel lines. Think for a moment, how would you describe parallel lines? You might say, well, they're two lines that don't touch each other or don't intersect each other. And yeah, that's essentially it, but we want to format it now into this very specific pattern of if and then. So here we go. If two lines are coplanar, that means together on the same plane. If two lines are coplanar and do not intersect, comma, then they are parallel lines. Alright, so our hypothesis is two lines are coplanar and do not intersect. And the conclusion is they are parallel lines. Notice, as a side note, that when we write these statements, we always start off with the noun, right? That's the object, that's the person, place, or thing. The noun is the person, place, or thing, and so that's what we start off with. It says if two lines, so we're talking about lines. So in the first part, in this hypothesis, you got to have the object, you got to have the noun. You can't just say if they intersect. That would not be clear. So we have to describe what it is. And then in the second part, in the conclusion, now we can use that pronoun, right? So the pronoun is in place of the noun. So we could use the noun again. We could say then the lines are perpendicular lines, but we could use that pronoun. Notice we're using the same pattern here with parallel lines. If two lines, there's my noun, are coplanar and do not intersect, then they, there's my pronoun, are parallel lines. You can always take that pronoun out and replace it back again with the noun if you want. Okay, here's our last example. There's really two. There's a segment bisector, there's an angle bisector. Let's just do one of the two. Let's just talk about the segment bisector. So you think about what a segment bisector is. Well, it's a segment that has been cut in half. So that's the basic idea, but how would we phrase that in an if-then statement? Let's try this. If a segment is bisected, comma, then the segment has a midpoint. So no, this is the actual definition. Notice it's not quite how we said it in a general sense. The way I described it generally, I said, well, if we have a segment that it is cut in half. Well, that's not technically true. If a segment is bisected, then it has a midpoint. Because then you could follow that up with the definition of a midpoint, which is, well, if a point is a midpoint, then it creates two congruent segments. So what we have here now is our noun. The noun is the segment. If a segment is bisected, then, and there's the noun again. So we could have written that with a pronoun. We could have said, then it has a midpoint, but I just happen to have the noun back in there a second time. So our hypothesis is this phrase, a segment is bisected, and the conclusion is the phrase, the segment has a midpoint. Alright, so there are some examples of conditional statements in this if-then form with identifying the hypothesis and the conclusion. There are some more statements that we have to write, and that's on the next page. So if you'll take a look at the top of the next page, we have one more vocabulary word right up here at the top, which is counterexample. You can see within that is the word example. So it is a type of example. So this is an example that proves a statement false. Because when we write statements in our proofs, we always want true statements. So we need to be able to determine sometimes if our statements are in fact true or not true. And so if it is a false statement, how do we prove it? We give a counterexample. It's an example that shows why it's not true. So we're going to do that here in example 4. Decide whether the conditional statement is true or false. If it is false, find a counterexample. So note that it is only necessary to show only one counterexample, because for a statement to be true, it must be true for all cases. Meaning, if it's true, it's always true, and if it's false, we don't have to show 3 examples of why it's false. No, we just show one example why it's false, and then we know the statement is false and it can't ever be true. Alright, part A. If the sum of two numbers is positive, comma, then the two numbers being added are both positive. Alright, so here's the hypothesis. If the sum of two numbers is positive. Alright, so we want to think about adding together two numbers, and we're saying the result is positive. So think some number plus some number, and my answer has to be a positive result. So now what we're claiming then is that that will always create the situation where the two numbers being added are in fact both positive. Alright, well, this is going to be a false statement, and I hope you recognize that was false. But now we have to prove it. Like, prove it! How do you know it's false? Well, we have to come up with a single example, and this is our counterexample. So, let me add up two numbers. And normally you might think of numbers like 2 plus 3. Hey, 2 plus 3 gives me 5, and that's a positive result. And the two numbers I'm adding are both positive. The 2 and the 3 are being added are positive. But we want to think of a way that we could add numbers that don't give me a positive result. Could we add up two numbers that give me a negative result? For example, what is a negative 1 plus a negative 2? Notice that this is not a counterexample because this first part must be true. The sum of two numbers is positive. Oops, I have a negative result. I did not match this first part. So this does not work as a counterexample. So let's think of a positive result. Alright, how about this? This is much better. So we're talking about the sum of two numbers is positive. Now I'm matching the condition. This is now true. And if this is a positive result, we're concluding, well, then that means that my numbers being added are both positive. Well, technically 0 is neither positive nor negative, alright? So that's the counterexample right there, using a 0. Here's another example. We could do this. How about a negative 1 plus 3, for example, right? So here we have met the condition. The sum of two numbers is positive. Yes, my answer is positive. We're claiming then that the two numbers that we've added together are both positive. Nope. There's our counterexample. That negative 1 is not positive. That's my counterexample right there. So I listed two counterexamples just to show you some variety, but really we only needed one counterexample to show the statement is false. Part B. If an angle measures 112 degrees, then it is an obtuse angle. So here's the condition. We must have an angle that measures 112 degrees. Then, does that make my conclusion true? Yes, it is an obtuse angle, and that is a true statement always. Part C is a little bit tricky. I'm going to break this down because of the way these are described here, but we're going to be talking about some numbers here. If a number is a power of 2, then it is a multiple of 4. Alright, let's think about what we mean by powers of and multiples of. So when we're talking about power of, this power is describing an exponent. So when we say power of 2, that means 2 is my base. So you want to think of it like 2 to the power of 1, or 2 to the power of 2, or 2 to the power of 3, or 2 to the power of 4. And that's what that phrase means. If a number is a power of 2. Okay, so what are those numbers? Well, 2 to the first power is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16. So when we say if a number, these are the numbers we're talking about. These numbers are the results of the power of 2. So that sets up the condition. Now here's the result. Then we're saying then it, meaning these numbers here, the 2, 4, 8, 16, then it is a multiple of 4. Well, 16 is a multiple of 4 because you can go 4 times 4 is 16. 8 is a multiple of 4 because you can go 2 times 4 is 4. 4 is a multiple of 4 because you can go 1 times 4 is 4. But this is not a multiple of 4. That right there, that's my counterexample. So we would say false. 2 to the first power is 2 is not a multiple of 4. Alright, part D. Now we have an equation. We're saying if 3x plus 10 equals 16, then x equals 2. Well, let's solve this and find out. Alright, subtract 10 from both sides. We get all of the constant terms on the right-hand side. Now we'll isolate the variable by dividing by 3, and we get 2. So my conclusion is true. So there were some if-then statements that had to do with some equations. We won't see those very often, or some numbers. We won't see those very often, but you can see that they apply to more than just definitions in geometry. Here's another very important vocabulary word that we'll be using today, and that is the converse. It's another kind of if-then statement. The converse is formed by switching the hypothesis and conclusion. Right, the converse is formed by switching the hypothesis and conclusion. Now, very important here, we'll see an example of this in just a moment. When we are writing the converse, you must start your sentence with a noun. And specifically, we will see in the example below, we'll see example 5b, where this is really made clear. Okay, example 5, it says, write the converse of the conditional statement that we had in example 4 up there, and then determine whether the converse is true or false, and if it is false, give a counterexample. Okay, we're going to write the converse, which is another kind of if-then statement, and we do that simply by exchanging places between the hypothesis and the conclusion. So for part A, we're going to use part A from the previous example 4. And I think it helps if you just take a moment and underline the hypothesis and maybe circle the conclusion like what we had done before. We're going to take those two parts and exchange their places, and that's what will make the converse. So it will say if the two numbers being added are both positive, then the sum of two numbers is positive. Alright, so we're going to switch those around and jot that down here. Okay? So if two numbers being added are both positive, comma, then the sum of two numbers is positive. This is my converse. If two numbers being added are both positive, then the sum of two numbers is positive. So we want to know if this is true or false. So think of the condition if two numbers being added are both positive. So we're focusing on the two numbers are positive and we're adding them together. So that means if I have a positive plus a positive, then the sum, the answer of the two numbers is also positive. That is true because any positive number plus another positive number will equal a positive result. And that's why. But it is a true statement. Alright, part B. This is the statement we had originally. If an angle measures 112 degrees, then it is an obtuse angle. So we're going to switch these around to create the converse. And it would look like if it is an obtuse angle, then an angle measures 112 degrees. So this is where we want to be careful. Remember, we always want to start with the noun, and if we take this hypothesis, which has a pronoun in it right here, the word it is a pronoun, it's in place of the angle, and we move this to the front, that means we're moving the pronoun to the front, and we would be starting with the pronoun. We would say if it is an obtuse angle. We don't want to say if it, because that's not precise enough. It's too vague. What are we talking about? What is this it? So we're going to edit this slightly to make it clear, and we're going to use a noun instead. We're going to say if an angle is an obtuse angle, then it measures 112 degrees. Alright, so let's do that now. If an angle is an obtuse angle, comma, then it measures 112 degrees. Alright, so there's your noun, there's your pronoun. So again, always make sure your sentence starts off with the noun. You could have noun, noun. You could say if an angle is an obtuse angle, then the angle measures 112 degrees. But you can't have pronoun at the beginning. Alright, so let's think about this. Is it true or false? If an angle is an obtuse angle, well, by definition, it could be anything above 90 and less than 180. It doesn't have to be 112 every single time. So this is false. Now we have to come up with a counterexample. We have to be specific. Don't say it could be anything between 90 and 180. No, no, no. We have to have one specific example. You could say the obtuse angle is 150 degrees. You just kind of make up a number that is within the range, but we're just claiming one other size. So don't say it could be something else. That's too vague. Don't say it could be an angle between 90 and 180. That's too broad of a range. Give a specific example. You're claiming it's something else. No, no, no. The angle is 150 degrees. I'm going to skip part C. Let's go down to part D. Part D was this equation here. So again, we're going to exchange the hypothesis with the conclusion. So it would say if x equals 2, then 3x plus 10 equals 16. What do you think about that one? True or false? This one is a tricky one. I asked this in class, and most of my students will say the answer is true because we just solved it, right? We solved the equation and we got 2 as a result. So if we go backwards, if x is 2, or if you take that 2 and plug it in, then of course it's a true statement, but the answer is false. And I'll tell you why that is by writing down my counterexample, right? If I'm claiming it's false, I have to give you an example for why it's false. And then I'll explain why we are thinking it in this way. So here's my counterexample. If x equals 2, then other statements, we mean other equations, right? Other equations, other statements are possible, such as 5x equals 10. So when we have this statement here, this conditional statement, what we're saying is that if x equals 2, then this is the only equation in the world that can possibly result from having x equals 2. And we're saying, no, this is not the only equation in the world. There are lots of equations in the world for which x can be 2. And this is my one counterexample to one other equation where it is also true when x is 2. So you have to think carefully about this cause and effect, this effect being like the only effect you get from that 2. It's actually quite similar to what we just saw in Part B, where we're saying if an angle is an obtuse angle, then its measure is 112 degrees. Well, yes, that is an obtuse angle, but that's not the only obtuse angle. There are many other obtuse angles, and here's one example of an obtuse angle, the 150. This is a very similar pattern. We're saying if x equals 2, then this is the only equation that exists. No. There are other equations that exist for which x can be 2 as well. So on the homework worksheet, you'll be writing if-then statements. You'll be determining if they are true or false, and you'll be identifying the converse, and if they are true or false as well.